This conference will now be recorded.
All right, good afternoon. My name is Greg Wadley with CTC & Associates. I'm the Clear Roads Administrator. We're here for an interim webinar for the project entitled Standard Test Procedures for Ice Melting Capacity of De-icers. This research effort is led by Xiaoming Shi at Washington State University. Before I turn it over to Xiaoming, I want to let everybody know that this webinar is being recorded. It will be posted on the Clear Roads website at a later date for your viewing and for your colleagues at your convenience. We also ask that everybody stays on mute today so that there's no background noise. However, if you have any comments or questions, please enter those into the chat box and we'll address them at the end of the presentation. So with that, I'm going to turn it over to you, Xiaoming.
Thank you, Greg, and thank you, everybody. Thank you to the Clear Roads Technical Advisory Committee. And this is a project update for the project titled Standardized Test Procedures for Ice Melting Capacity of De-icers. The research team included myself, Xiaoming Shi, and also Dr. Mahdi Nazari and others at WSU or Washington State University, as well as Paul Braun and Dave Barnager. Now, so see how I advance. Okay, now just to refresh your memory, the objective of the project was to evaluate the suitability of the mechanical rocket test as a standardized lab test that can realistically and robustly assess the performance of de-icers so as to enable data-driven procurement decisions. So just a little bit on the test protocol itself. As you can see, we started with two groups of cups. Each group consists of 5 cups because we are trying to do 5 replicates. And then you also end up with the numbers, 5 of them again. And then we basically dispense the deionized water into the ice cube trays, and then also make the ice cubes, and then disperse the liquid de-icer into the thermos labeled. And then what we do is to place them in freezer and make ice cubes, and then basically weigh them and then mix the ice cubes. Add ice cube into the thermos, and then take about 15 minutes to have a mechanical rocking test, and afterwards measure the ice melt versus the amount of the ice applied. Oh, one thing I should mention is the ice was then sieved so that we can separate the liquid from the solid phase, and then measured and weighed. So this procedure is different than the shop ice melting test. One advantage, supposedly, conceptually, is to introduce the mechanical agitation so that it's more realistically simulating what's happening in the field scenario. So the project is tasked to evaluate, the reproducibility, repeatability, and the other aspects of this test protocol developed by Nebraska. So so we mainly use 2 STM standards. The first one is to examine the precision of the test protocol, which included the single operator precision, also known as repeatability, and also multi-laboratory precision, also known as reproducibility. And another aspect is the ruggedness of the test, which helps us to determine which factors may or may not have a statistically significant impact on the test results, which is the ice melting capacity. So we'll get to that. Starting from the precision, you can see STM E691. If you look at the top on the left-hand side, you basically have this so-called one cell, which is the 5 replicates of a single liquid de-icer, and tested by a lab where you get 5 readings, and then you have the average. On the right-hand side, the equation 2 is look at the standard deviation of the cell. And then you move down to equation 3, where you're looking at basically the average is from different labs. I should mention that in the second round robin test, which we're talking about here, we involved 10 different liquid deicers. Each one had 5 replicates, and then we also involved 8 peer labs to do this round robin test. So between different labs, they have different average values. So then you can get the average of the average values, which is equation 3. And then you can also calculate for each lab how far they're deviating from the average of the average. So and then you can calculate the standard deviation of the cell averages, which is the equation 5, and the repeatability standard deviation equation 6, and so on. So you know, again, these data points, again, from 8 different labs, each dealing with 10 liquid deicers, and each deicer having 5 replicate measurements, then gives us a lot of insight about how statistically reproducible and repeatable they are. Again, repeatability is dealing with within the single lab, and reproducibility is really talking about across labs. So if we aim for 95% confidence level, then we can calculate a threshold for what's acceptable repeatability, which is the small r equals 2.8 times standard deviation of small r, versus the reproducibility, which is the capital R equals the 2.8 times standard deviation of the capital R. So with that, you can see, for instance, the 10 different deicers. If we look at the first deicer, which is a analytical grade salt brine, 23% by weight of the solution, and what you end up is for each lab you can obtain the standard deviation of the test results, and also again what's acceptable repeatability and acceptable reproducibility are shown here. As long as your standard deviation is smaller than the thresholds, in this case that is the case. Standard deviations for each of the 7 labs here are smaller than acceptable repeatability threshold and acceptable reproducibility threshold. That means, okay, for the 23% sodium chloride solution at least, the test is considered statistically repeatable and reproducible. Now, going on, basically for each other deicer, we found the same thing. For the 32% calcium chloride, for the 29% mag chloride, again, the test protocol has demonstrated really high repeatability and high reproducibility. So moving on to the other types of deicers identified by the Technical Advisory Committee under the Clear Roads Pool Fund. Again, different deicers showing further confirming, the standard deviations are within the range. So therefore, the test protocol is highly repeatable and reproducible. So I'll go really fast on these numbers, but basically they're telling exactly the same story. The test protocol is, very precise in terms of within lab repeatability and between lab or cross lab reproducibility. So yeah, so these are the 7 commercial liquid deicers plus the 3 analytical grade chemicals. Now, another aspect is the ruggedness of the test protocol. Is the test too sensitive, to any sort of parameter in the process? The ideal situation is that it's not sensitive, therefore it's it's very robust. The test is STM C1067, and basically we're comparing the variance, and the type of parameters we look into include, thermal shape, the ice cube shape, ice cube volume, rotational speed, tilt angle, testing duration, and operating labs. Whether or not any of them would have a significant impact on the test result. So starting from the shape of the thermals, we had two different types of thermals. One is short, one is tall. You can see that in the next slide. So basically, we're required to test 4 representative de-icers with this variation and then compare the results. If we conduct the so-called ANOVA or analysis of variation, analysis of variance for the ice melting capacity data, you can see the p-value here is close to 0.74, which is much greater than 0.05. Again, if the p-value is greater than 0.05, that means the difference between different groups is not statistically significant. So in other words, switching from the short thermals to the tall one did not really induce a significant difference in the test results. Now, what about the ice cube shapes? We again conducted these tests. Remember, for each de-icer, for each bar, there's a standard deviation. That's because that's the summary of 5 replicates. So again, we conducted a novel analysis for the ice melting capacity data. The p-value again is much greater than 0.05, which means the difference between these 2 different types of, the shapes of the ice cubes was statistically insignificant. Now, what about the ice cube volume? Because we play with 2 different types of volumes. One is 0.85 milliliter versus 1.3 milliliter. And again, the p-value is much greater than 0.05. That means the test result is not sensitive to this variation in the ice cube volume. Now, what about rotational speed? We look at 2 likely rotational speed, one is 70, one is 90. With that variation, again, we conduct this ANOVA analysis. The p-value is greater than 0.05, meaning the rotational speed is not a significant factor for the ice melting capacity result. Now, for tilt angle, we explore the difference between 8 degrees and 10 degrees. Again, the test result is indicating that the tilt angle doesn't have a statistically significant effect on the ice melting capacity data. Now, test duration, we compared between 12 minutes and 15 minutes. And again, the results the same. P-value is greater than 0.05. Therefore, the test duration between 12 minutes and 15 minutes did not make a significant difference. Now, what about operating lab and operator? Actually, earlier I mentioned, all these results report here are from our second round robin test. In the first round robin test, we actually had confirmed that the operator did not make a significant difference. But there were some quite unusual data points, and we end up, with the guidance of the technical panel, we decided, we should move from 3 replicates to 5 replicates. That's why, this set of data is much more reliable. And also we implement some additional quality control to remove some abnormal data points, so the results are more trustworthy. So for instance, one way to look at the data filtering, when we receive the raw data from a single lab, for instance, if from the lab, the coefficient of variance in the data set is greater than 10%, then those data points were removed, and also we used STM 802 to identify outliers and remove the outliers. That's one level of quality control. And then because we had a lot of data points from these 8 different labs, so we were able to estimate a value which is closer to the actual mean, because there's no way to measure the actual mean or even theoretically calculate the actual mean easily. So then we use the total data set to get to a median, which is very close to the actual mean. So that's a way we use the median plus minus 1 standard deviation. Sorry, actually there's a typo here. It should be 2 standard deviations. Then anything outside of that range we consider as erroneous. So those data points were removed. So in doing that, we actually end up with less data. So for instance, you can see for the sodium chloride based liquid deicers, we tested all of them under 15 degrees Fahrenheit. Actually for the magnesium and calcium chloride based deicer, we tested them at 0 degrees Fahrenheit. So for each group, we end up having 5 sets of data instead of all 8 sets of data, because some of the data points were not well, basically they failed to pass the quality control procedure. So if we take the individual measurements of each lab and evaluate whether or not the operating lab had a significant difference, unfortunately, you can see here, even though the top one's looking at the sodium chloride based deicers, right? So the p-value, even though it's greater than 0.05, but it's really, really close. So it's kind of implying there may be a significant difference by the labs. Now, the second one, when you test things, I mean, the calcium and mag chloride deicers under a colder temperature, which is 0 degrees, then it's even more sensitive to the testing labs. So then we look at the data and think from the practical perspective, what we really care is whether or not the reported numbers from different labs would be significantly different from each other. In that case, the reported value is the average. So when we test the average, the situation is a little bit, well, is much better. So for instance, at 15 degrees Fahrenheit, the p-value is significantly greater than 0.05. In other words, there's no statistical difference between different labs. When you look at the 0 degrees for calcium and mag chloride deicers, the p-value 0.066, so greater than 0.05, but still somewhat sensitive. There are 2 possible reasons. One is at a cold temperature, the amount of ice melted is less. Therefore, the variation is higher in terms of measurement error. But the other thing is really when your thermals are under much cold temperature, they're more sensitive to the disruption, from the ambient temperature, when you're opening, when you're operating in that process. So to conclude, we would say that the test protocol performed well in both precision and ruggedness, even though, as I mentioned earlier, there's a little bit of concern about the cross-lab variability. And then also change in ice melting capacity due to different rotational speeds, mechanical rocket types, tilt angles, test durations, and operating lab are not statistically significant, especially if you look at the reported value, which is an average value, not the individual 5 data points. Actually, that tells us, part of the variation came from this relatively high coefficient of variance. In the beginning of the test, we debated whether or not we should go with a much lower coefficient of variance, lower than 10%. I think we agreed that we'll take all the data points which are within 10% COV or coefficient of variance. In implementation, we probably would be a lot more stringent and lower that 10% down to something like 6%. Ruggedness tests show that ice melting capacity values do not change significantly due to change in the shape of the thermals or the ice cube or the volume of the ice cube. Now, the operating lab is the most sensitive variable in this research. Again, especially when we try to test it at a lower temperature like 0 degrees Fahrenheit. Now, to minimize the inter-laboratory variability, we incorporate 2 data acceptance checks. The first one is coefficient variance, like I mentioned earlier. During the first and second round robin tests, we use 10% as the threshold, but we would recommend 6%. That will help reduce the variability. Now, again, from the first round robin test to the second one, we moved from 3 replicates to 5 replicates. That really helped the results to be much more consistent. Also, we already implemented 2 certified reference values. Based on all the data points collected, we were able to approximate an actual mean, which for the sodium chloride brine, analytical grade tested at 15 degrees Fahrenheit, it's this range, 0.146 plus minus 0.094. Again, this is the statistical medium plus minus 2 standard deviations. And for the magnesium chloride analytical grade tested at 0 degrees Fahrenheit, the range allowable was 0.384 plus minus 0.098 gram per milliliter. So with these internal, the built-in quality controls, then we should get much more reliable results. Again, one thing we did not implement in this second round robin test was the 6% CLV, because if we had done that, then we would end up with significantly less data points to enable the statistical analysis. That's all, and thank you for your attention, and hope to have some questions and discussion. Thank you.
All right, thank you, Sean. Right now, I don't have any questions or comments, but I guess I would be inclined to open it up. Since we're done with the presentation, if anybody has a question or comment, feel free to unmute yourselves and ask your question.
Hi, this is Cliff. Doesn't look like my camera's working, which is okay. When I was looking at the bar graphs that you had, where there was a difference in what the labs were doing, but yet they all seem to be very relative to themselves. Are we so hyped on the fact that our labs are different, or is it just that statistical analysis is more important because they follow the same procedure? Maybe I missed something in there. Sorry, Xiaoming, if I did.
Right.
Just wondering which is more important, the consistency of the lab or the consistency between labs?
Actually, both of them are important, but at this point, what we can say with more than 95% confidence is that very consistent, within the lab, even if you change operator, everything is very consistent. But between labs, there's some details we actually further suggested to improve the reproducibility between labs. For instance, like this coefficient of variance threshold of 6%, because as I showed earlier, when we compare look at the effect of operating lab, basically when you look at individual values, they're saying, hey, there's a significant difference, especially at the cold temperature between labs. But when you look at the average, that difference is diminished because, again, within labs, the variability is too high when we look at the 10% as our coefficient of variance threshold. So that's where, the test protocol really needs to specify a more stringent acceptance value. Again, in this case, for instance, we just remove the data points which are, failing the quality control level 1 or level 2. But in the implementation, if somebody submit a data set which gives you coefficient of variance higher than 10%, I think we agree that we'll just have to tell the lab, say, go back and redo the whole set of testing because something was not right. but in this project was kind of impractical because there was a lot of delay and coordination. So we couldn't tell people to go back and redo everything. So we just removed the data points which are beyond 10%. So in other words, with more stringent quality control, I think, we probably will be, better off. I'm not sure whether that answers your question.
Yeah, yes, it did. Thanks very much, Xiaoming.
One thing I also want to clarify, sometimes you see the bar graphs. Well, I'm trying to find an example. For instance, the effect of ice cube volume. You look at the ISA, you'll be like, well, there's definitely a difference between, the 0.85 milliliter versus 1.3 milliliter. But when you look at the test protocol as a whole, like across different deicers, statistically speaking, then there's no difference. So mostly we're focused on the evaluation of the test protocol. In other words, some of the deicers are more sensitive than others. Of course, in the test protocol, we specify, what type of ice cube and what volume, what thermal type we should use. Just to, the more details you specify, the less likely they will deviate from the test protocol and introduce additional variability.
So, well, thank you for that, Xiaoming. The Laura Shanley from Illinois asked a question: will all the data be in the final report? And that is, in fact, true. It will be. I know I can answer you in that one. I'll get to Scott here in a second. Scott, I know your hand is raised, but Laura came in with a second question sort of together. So her other question was there a common area in the test where difference occurred?
Sorry, I didn't really quite get the answer. I mean, the question, is it in the chat box?
Yeah, it's in the chat box. It says, was there a common area in the
chat box
test where the difference
So,
occurred?
will all the data be in the final report? Yes, definitely. Actually, when I was preparing the slides, I realized we had a minor mistake error in the past two report. I'll update that and also address Jasmine's comments as well. So we'll be sending the updated report in a few days. And another question was from Laura, was there a common area in the test where differences occurred? Common area, I'm not sure what you mean.
Laura,
okay, can you guys?
You want to come off mute? Oh, there you go.
Okay, so what I'm saying is, when you were data coming in, was there a certain weight, was there a certain part within the test that was where you were seeing the error? So when you looked in and be like, and again, my background was a lot more with running like specific gravities on asphalt bricks and stuff. And from there, it would be like, it was the surface dry weight versus this weight versus that weight. So my question here is, when you see these differences between the labs, where are you seeing cause? What is the pinpoint? Is there a common area, or is it just a variable of random?
Yeah, that's a good question. I think, again, if you look the data, test at 15 degrees versus 0 degrees, you can see 0 degrees definitely is much more sensitive to, human error or anything like that, or between labs variability. So we certainly talk about, better insulate the thermals as a possibility, but also actually not every lab follow the instructions. For instance, one of the labs, they tested things at 10 degrees Fahrenheit. We had to remove the entire data set, even though we told them, which temperature, but they did not follow. So it was unfortunate. And then if you look at I probably should not mention which lab, but one of the labs, they actually use a different kind of rocker type. So their variability was much higher. I mean, the variability within their own data points. So we end up only using partial data from there, because once we treat the data through the quality control level 1 and level 2, almost half of the data points are removed. So, the devil's in the details. If they truly follow the test protocol, the results are much better and consistent.
And I would take it that that would be a finding too, is that, you know, we put out a test procedure and there was that variation. So that's a negative and a concern. That, I mean, is there a reason why it was hard for them to follow? You know, what was, you know, if it was equipment, that's one thing. If it was they just couldn't follow directions, and that's another, again, it's a little, yeah. No, that's good information. And I guess my other question too is, because it was a lot of data at once. Did you notice were more aggressive de-icers, more variable?
That's a very good. That's a very good question. We can look into that. I didn't really focus on that, but I'm sure there's some de-icer which would be more sensitive. Yeah, we can look into that and get back to the team. All conceptual. Well, again, our hypothesis would be, you know, the organic de-icers, I mean, might have more sensitive behavior, but we don't know for sure. We'll look into that.
So then Scott Lucas had a question. Scott?
Yeah, I wanted to just make sure you can hear me okay.
Yep.
If you can't, okay. New computer, just make sure everything's set up right. But yeah, Xiaomi, I was just kind of curious about your feeling on, and it's just, I guess there's some assumptions there with AASHTO and what they were asking about the project. Is there anything that they've mentioned about having to tweak anything, or do they give you any information about how they felt about it moving forward in the process?
Right. Maybe Jasmine, you are more in the loop on that one. Could you update the AASHTO feedback?
Yeah, that is a great question. I have not heard anything from my supervisor yet. That committee, the balloting is still going on, I believe, for maybe another week or so, week and a half. And then that's when we'll see any negative, excuse me, comments or questions. So that will be maybe another week or two out.
Thank you. Yeah, I was just curious. Go ahead. Sorry.
You know, one thing I want to share is this is many years ago, back in 2004, I think, maybe 2003. You know, Pacific Northwest Snowfighters Association organized a corrosion forum because the dipping test, you know, the corrosion test, which was standardized by NACE and then later adopted by PNS for testing corrosivity of de-icers, as a standardized test, actually has a lot of issues. So you can see, you know, again, the variability, especially between labs, usually come from little steps which were not clearly specified in the test protocol. So that's one thing we learned is like the more, you know, details added into or specified into the test protocol, you know, the less likely you will have variability across labs. In the corrosion case, it was partially because of the highly sensitive nature of corrosion. I mean, to where the coupons came from. I mean, the metal coupons, because if they had gone through some sort of unusual mechanical or thermal history, then you know, the corrosion numbers were different. So, but in this case, one thing we talked about in earlier meetings was, you know, make sure the room was, I mean, the temperature measurements are correct, because if they're off by 1 degree, then, you know, you will see consistently different results, right? Like, even though within the data it's very consistent, it's probably will pass the coefficient variance test. But the hope is that by building in those two internal values for the 23% sodium chloride and the 29% mag chloride, if the temperature sensor was off, then most likely they'll fail that test. Therefore, the, you know, measurements will be rejected. They have to go back and redo the test.
Thank you. Appreciate that.
All right, thank you, Scott. All right, anybody else have any questions or comments to this point? Okay, hearing nothing. As I said before, I will go ahead and post this on the Clear Roads website, the project page, and I'll alert you when it is up there. And as Sean Ming had mentioned, and Jasmine also mentioned, this project is still it's still ongoing. We're still sort of refining this draft or this final report that documents this process. Excuse me, and we are still in the process of ushering this through the ASHTO committees, as Jasmine had noted that they are going to be, and also noted during our fall meeting, that they're going to be going through the Materials and Pavement Committee balloting. They're going to meet again, I think, in November, and then if it gets passed by them through for recommendation to the rest of the committees, then it'll go through concurrent balloting next summer, and then assuming approval, then it would be published in 2024. So that's kind of where we're at right now. Is that correct, Jasmine?
You got it, Greg.
Okay. All right. Well, thank you again, Sean Ming. Thank you for everybody for joining us, and have a good rest of your day.